Alright, welcome back everybody. In this video we're going to discuss information from section 8.3 of AP Calculus using accumulation functions and definite integrals in applied contexts. If you remember from the fundamental theorem of calculus, you should remember that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F of x is the antiderivative of lowercase f of x. What this means is that the integral of a function is the net change of its antiderivative. It's the difference between where the antiderivative was at the starting point minus where the antiderivative was at the ending point. And both of these equations represent that in slightly different forms. You know, here we start with the integral as the integrand as lowercase f of x. Here we start with the integrand as lowercase f prime of x, but in essence these two statements say the exact same thing. The integral of the derivative is equal to the net change in the antiderivative. So this is one of those things that I think is hugely important. I mentioned this in the last lesson in section 8.2 when we talked about the position equation that I showed you. The position equation that we talked about in section 8.2 is just another form of this crucial relationship that everybody needs to know and be able to use. I would bet that there's at least a handful, 3, 4, 5 questions on your AP exam every year that are going to incorporate this net change relationship. And basically I've taken this equation and manipulated it algebraically to go down here, and this equation and manipulated it algebraically to go down here. But in any case, what we've got in both of these is we've got the unknown value is equal to the known value plus the net change. And same thing for this other one. The unknown value is equal to the known value plus the net change. And we're finding net change by taking the integral of the derivative of whatever we're trying to find the change of. So this relationship is really huge. Like, it enables us to go to any unknown value as long as we have one known value and the rate of change, the derivative. All right, so let's go ahead and we'll put this into context. We're going to start here with example 1. Example 1 is from the 2018 AP Calculus AB free response question number 3. This is a non-calculator question. And we're going to do two parts of it, one of which deals with net change and the other one which doesn't as much. All right, so here we go. The graph of the continuous function g, the derivative of function f, is shown below. The function g is piecewise linear for this interval and is equal to g of x for 3 to 6. Okay, if f of 1 is 3, what is the value of f of negative 5? So we have an unknown value that we're trying to find. That's equal to the known value, which we know the value of f of 1, plus the integral from the x-coordinate of the known value up to the x-coordinate of the unknown value of the derivative of this function. And we're told in the lead-in that g is the derivative of f. So we want the integral here of g of x dx. Now, one thing is stopping us from, moving directly forward, and that's the fact that these limits of integration are out of order in this case, since we're moving to the left. So I'm going to go ahead and change this. Using my integral properties, I'm going to bring a negative sign out and flip the limits of integration so that I can treat this as an accumulation function of the graph. And now it's just a matter of calculating. F of negative 5 is equal to f of 1, we were told, is 3. And then the integral from negative 5 to 1 is all area-based here. We've got this area right here, which is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.5 units, that are below the axis, so that's negative 10.5, that it contributes to the integral. And then we've got 0, and then we've got this area right here, which is a triangle with an area of 1. That's positive. And so this ends up being 3 minus negative 9.5, or 12.5, for the value of f of negative 5. Okay. Part B of this question, pretty straightforward, just asks us to evaluate the integral from 1 to 6 of g of x. The thing that's not straightforward about this is that we have a piecewise function that's split into two parts. So what we've got is we've got to find the integral from 1 to 3. Since that's the piecewise portion, the piecewise linear portion. And then we've got to add to that the integral from 3 to 6, which is based off of the equation that we're given for the interval from 3 to 6. All right, so this is going to be equal to 4 plus the integral from 3 to 6 of g of x dx. So that's the integral from 3 to 6 of 2 times the quantity x minus 4 to the second. So I'm going to go ahead and find my antiderivative. It's going to be 2/3 times x minus 4 to the third power, evaluated from 3 to 6. We've got 4 plus 2/3 times 2 cubed minus 2/3 times negative 1 cubed. So that's 4 plus 16/3 plus 2/3, and we end up with the value of that integral being, it looks like 10. Yep. Okay, on to the next page. Example 2 from the 2017 AP Calculus AB exam, free response question number 2, calculator. When a certain grocery store opens, it has 50 pounds of bananas on a display table. Customers remove bananas from the display table at a rate modeled by blah de blah for time 0 to 12, where f of t is measured in pounds per hour and t is the number of hours after the store opened. After the store has been open for 3 hours, store employees add bananas to the display table at a rate modeled by g of t equals blah de blah for 3 to 12, where g of t is measured in pounds per hour and t is the number of hours after the store opened. Part A. How many pounds of bananas are removed from the display table during the first 2 hours the store is open? So this is just asking us how much is removed. And so that's just going to be an integral of the removal function, which is, in this case, f. Okay? Customers remove bananas based on f during the first 2 hours the store is open. So we're going to just take the integral from 0 to 2 of f of t dt. And I'm going to go ahead, this is a calculator problem, so I can go ahead and do this on my calculator. So I've got the integral of 10 plus 0.8t times sine of the quantity t cubed over 100 with respect to t from 0 to 2. Let my calculator handle the calculations here for us. And we get 20.051 pounds. Okay, not too bad, pretty straightforward. Just integrate the rate at which they're removed. And part D is where this gets interesting. How many pounds of bananas are on the display table at time t equals 8? So this is a little bit different from our basic net change idea. What we've got is we're trying to find out how many are on the table at time 8. The amount at time 8. I don't have a specific function representing the amount of bananas, but the amount of bananas at time 8, which is the amount that we had at an unknown time, or at the amount that we had before. At the beginning, there's 50 pounds of bananas. So that's at time 0. Now in this case, we don't just have one function that's operating on the number of pounds of bananas on the table, we have two. One that takes bananas away, which was f of t, and one that adds bananas to the table, which is g, but g only starts at time 3. So we need to start adding bananas at time 3. And now this whole expression is going to tell me the amount of bananas at time 8. There were 50 to start, minus the integral from 0 to 8 of f of t, which I'm just going to type in on my calculator, plus the integral from 3 to 8 of g of t. I'm going to type this whole thing in on my calculator, and it's going to give me my value. So I'm going to have 50 minus the integral of f from 0 to 8 plus the integral. Now I need my function for g of t, which is 3 plus 2.4 natural log of the quantity t squared plus 2t with respect to t from 3 to 8, or our limits of integration on that one. And if I do all of that, it should tell me the total number of bananas on the table. My calculator's really grunting and straining. Alright, so let's make sure I type that in correctly. 50 minus the integral from 0 to 8 of f of t, plus the integral from 3 to 8 of g of t, and we end up with 23.347 pounds of bananas that are on the table at time 8. Okay, that's where we're going to wrap it up here. We're going to come back for a second video on this topic where we're going to work through one more example. Should be a fairly short video compared to this one. Alright, see you everybody. Have a good rest of your day and enjoy yourself. Bye-bye.